So we use the rearrangement lemma. Okay. So, so suppose we are given a non-unitary representation of G. Suppose there exists a, and whenever we talk about representations in this course, we mean finite dimensional representation. Because they are matrices, we're talking about matrix representation. Suppose there exists a non-unitary representation of G, given by the matrices d tilde of G. Okay. So these are not unitary. So the idea is to construct a unitary representation. Okay. So let's consider an object which we call H, and H is going to be sum over all the group elements of d tilde dagger of G, d tilde of G. Okay. Now, it should be obvious that H is Hermitian. Because if I take H dagger, of course, taking the adjoint, the dagger, the Hermitian conjugation commutes with the sum.
So what is capital H?
We are defining capital H to be this thing.
I mean, is it a group element?
It's a matrix.
Oh, okay.
I mean, these are matrices, right? These are square matrices because they are linear operators, right?
Yes.
So its dagger is also a square matrix. So this is also a square matrix, right? Okay.
Okay.
So so H dagger is taking the dagger means that we have D dagger, D tilde. I'm not writing the argument anymore. So this becomes, so we see that H is a Hermitian matrix. Okay. Okay, the next thing we will show is that H is invariant under the following transformation. Invariant in what sense, you ask? Well, if I take d tilde dagger, which is a function of, say, G prime, H is, of course, not a function of G because we have summed over all G. So the dependence on G has been summed over or integrated over. But if I take particular G prime and I do this sort of similarity, quote unquote, transformation, then using the definition of H, we get that there is a sum over G and there is a d tilde of G prime, and the definition of H involves d tilde dagger of G, d tilde of G, and then d tilde of G prime. Now we are dealing with representation. It is not unitary, but it's representation nonetheless. So we can write this as, this guy is basically going to be D tilde GG prime. And this thing, inside a dagger, the ordering will change. And therefore, this thing is going to be D tilde GG prime dagger, G tilde GG prime. And by the rearrangement lemma, we know that this is going to be the same as D tilde of G dagger D tilde of G, which is the same thing as H. So we see that H is invariant under this transformation, when, for an arbitrary G. Okay. Is this clear so far? All right. So since H is Hermitian, that means that we can diagonalize H by a unitary transformation. So we can say there exists a unitary operator W such that if I conjugate it, if I take a similarity transformation of H, then we get a diagonal matrix, and let's call it matrix rho squared. Okay, we shall see it's a squared matrix. It's all the eigenvalues are positive definite numbers. Okay, I haven't proved it, but let this be just the definition of rho squared, but it's diagonal. Okay, so let me not use D, but so this is a diagonal matrix. Right, you know this, right? And this is unitary, meaning that W dagger W is 1. Okay. So H has real eigenvalues, right? Why does H have real eigenvalues?
Because it's Hermitian.
Okay, is that something that everyone knows here? Is there someone who doesn't know this and needs to be shown? Okay, you should have learned this either in quantum mechanics or in linear algebra. Okay, so this is one of the most fundamental results of linear algebra. If you have a Hermitian matrix, its eigenvalues are real. Okay? That's why that is one of the reasons that makes in quantum mechanics the fact that observables are these Hermitian operators. Therefore, when we do experiments, we get real numbers as a result. Okay. So H has real eigenvalues because it's Hermitian. But it can also be shown that the eigenvalues of H are positive definite. They're either 0 or positive. And let me just first, motivate this. So for example, suppose that you have an operator whose form is, say, M dagger M, right? H has that form, right? There is just a additional sum, but H has roughly, this form, right? So now suppose that M acts on some vector and gives you another vector, M prime, psi prime. And then M dagger acting on psi prime gives you back the original vector up to C, right? So if I write this out, then I get M dagger, M acting on psi gives me C of psi, right? In other words, this is some sort of a, this is an eigenvalue equation. Give me just 1 second, just 1 second.